everyone! In this shorter video, we're going to discuss how to select an appropriate base to form your enol or enolate intermediate. So last time we talked about how alpha carbons are one position away from a carbonyl group, and alpha protons are relatively acidic. So in this case, the pKa of those protons is about 19.2. Then we said that if we react this with a base, that base is going to grab onto one of those alpha protons or deprotonate the ketone. We're going to leave electrons behind and form a double bond. And that's going to push pi electrons up to oxygen. So then we end up forming our intermediate here and a conjugate acid of our base. Now, ideally, we want the pKa of the conjugate acid to be greater than the pKa of our starting material. So we want the pKa of the conjugate acid to be greater than 19.2 in this particular case. In fact, we would actually like the pKa to be about 5 units greater than the pKa of the starting material. Otherwise, let's say the conjugate acid had a lower pKa than the starting material, then that conjugate acid would be more acidic, right? Because the lower the pKa, the more acidic something is. The more acidic something is, the more likely it is to give away a proton. So the conjugate acid would give up its proton to that negatively charged oxygen, and we would actually see the reverse reaction occur. So in order to favor those products, the conjugate acid has to be a less strong acid or a weaker acid than the starting material. So that means the pKa has to be higher. So let's just make a note of that. We'll just summarize here. So the pKa of the conjugate acid should be greater than the pKa of the starting material to favor the products. Okay, so let's look at some examples. All right, so last time we looked at this diketone here. And we said that if we added a base, that base would likely take protons from the central carbon because those will be the most acidic. And in fact, their pKa is about 9. So let's see if we can find a base that is appropriate for this reaction. But first, let's draw the product. So we know that a base would take one of those two central protons. Those are the most acidic protons on the molecule. And we would end up forming an enol. So again, we saw this on our last lecture. And let's also figure out what our conjugate acid would be. And remember, we want the pKa of the conjugate acid to be greater than the pKa of our original acid. So maybe take a minute, see if you can find a base that would be appropriate for this reaction. Okay, so in your textbook, you do have some tables of pKa values, or you could look up pKa values of different acids. And probably the easiest base that we could use is the hydroxide ion. because its conjugate acid is water. And the pKa of water is about 15. So that is definitely 5 units greater. It's actually about 6 units greater than the pKa of the original acid. So that works out. Okay, so you can't quite get rid of those pKa values. I know we keep bringing them up. They are important, especially in reactions like this one. Now, let's look at another case. Let's say that we have the same ketone that we had before. So we know that there are alpha protons that are fairly acidic, and their pKa we said was 19.2. One option we could use is called lithium diisopropylamide. So let's just draw that out, and I'll also write the name down. Okay, so we've got a nitrogen atom with 2 isopropyl groups, and that nitrogen is negatively charged, and then it's balanced out by, whoa, it's balanced out by a lithium ion. Now, one issue if you do have a negatively charged atom like this nitrogen, there could be a competing reaction, right? So we do have the potential here for that nitrogen to attack the carbonyl carbon. Or it could also act as a base and take a proton. However, we have those isopropyl groups attached to our base, and those are pretty bulky. So those bulky groups actually prevent nucleophilic attack. So the nucleophilic attack doesn't happen, and that nitrogen will just act as a base and take an alpha proton. So then we end up forming our desired products here, or intermediates. So we've got our enolate, and we also have the conjugate acid of our base as another product. And the pKa of this conjugate acid is about 38. So that is definitely higher than the pKa of our starting material. So that will definitely favor the products. Okay, and then let me just write down the name of this base. So again, this is called lithium diisopropyl. So we have 2 isopropyl groups, and then amide. And we can actually abbreviate this as LDA. So this is a really good base to use for alpha carbon chemistry because you'll preferentially take an alpha proton. You avoid that nucleophilic attack that could potentially occur. And the pKa of the conjugate acid is really high. So that will definitely help us move towards the products and will avoid a mixture at the end. Okay, so I think that's all we'll cover for this video today. In the next video, we'll start talking about alpha carbon chemistry. So what kind of reactions can we do with that alpha carbon? I will see you then.